Hello students, are you ready? Let us state and prove theorem 3.5, the basic properties of determinants. Number 1, multilinear. Number 2, alternating. And number 3, the identity property. What do you mean by multilinear? As you can see, the linear combination ax plus by in the jth column is being separated out, as you can see in the right hand side, and leaving all the other columns exactly the same. So this is basically the linearity in jth column only. And how many columns are there? There are n such columns. So this is basically n linearities put together. That's what we call multilinear. Now how about the alternating property? If I switch any two columns, then the determinant becomes negative. Here's an immediate consequence of the alternating property. If those two columns are the same, then even after switching those two, there's no difference, stay the same. So what real number stays the same after taking the negative? That's only 0. So whenever we have two identical columns, the determinant has to be 0. And that's one of more important applications of this alternating property. How about the identity property? Well, the multiplicative identity of real number arithmetic is 1, and the multiplicative identity of matrix multiplication is I, so they're related, and of course, indeed they are. Alright, we'll have to prove those, but before that, before any of those proofs, let's have some warming up. Let's go to section 3, and then let's go to the similar problem here. For 2 by 2 matrices and the determinants of order 2, we can define it like this, and we have these properties: bilinear, alternating, and the identity property for order 2. How do we prove? Well, this is the simplest. Just straight ahead calculation of the determinant, and we have 1. This one is almost equally as simple. The original matrix AD minus BC, that's the original determinant. Now what if I change the columns here, and we have this new matrix, and what's that determinant? It's BC minus AD. So one is negative of the other. Just one liner, pretty simple. Okay, let's move on. And how about the bilinearity? Is that really worthy of our time? Well, to a certain degree it is, so let's go ahead. Ax plus by here can be rewritten like this in the column vector forms in 2 dimensions. And the other column vector, let's keep it the same and put them together as 2 by 2 matrix like this. After, linear combination, you can add them all up and then put everything together. Then we have this matrix form. So alright, go ahead with determinant computation, crisscross AD minus BC form, and here it is. And then you can apply some algebraic manipulation to get this and that. But if it is a little bit hard to follow, then you can start from the last part, the determinants, and calculate this determinant and that determinant using those crisscross AD minus BC form. You get this and that. So comparing this and that, are they equivalent? It's tedious, but it's not too difficult. So I'm going to leave that to you. The answer is of course yes, and we completed all these for 2 by 2 matrices. Okay, how do I do this for n-dimensional matrix? N-dimensional square matrix. We're going to use the mathematical induction. The base case, n equals to 2. Actually, we are done. Alright, okay, let's go to inductive hypothesis now. Let's assume D1, D2, and D3 are all true for all determinants of order n-1. And then, based upon this inductive hypothesis, we'll prove all these, D3, D2, and D1 in that order, for the determinants of order n. Now, how do I use the determinants of order n-1 from the determinant of order n. If you take the deleted matrix, then that's going to be a square matrix of order n minus 1, so you're going to end up with determinant of order n minus 1. Consequently, the inductive hypothesis. So the key is deleted matrices. Okay, alright, here's the third. The determinant computation for the identity matrix of order n. Let's look at the first row. 1 times the determinant of the deleted matrix, and then all these are zeros, so we have a bunch of zeros. They all drop down. Now, 1 times this determinant. However, this determinant is the determinant of identity matrix of order n minus 1. So the inductive hypothesis applies. So that 1. So what do you have? 1 times 1 minus bunch of zeros. Okay, we have 1. Alright, next is D2. First, let us consider 2 adjacent columns, and then we're going to calculate all these and then prove the alternating property for 2 adjacent columns. And then we're going to extend it over to arbitrary case. Alright, let's begin with matrix A, an n by n matrix, and then let's select jth and j plus first, and then switch them. So jth becomes j plus first, and j plus first becomes jth. And we did some color coding, so you can easily see it. Alright, my aim is to prove that determinant of A is equal to negative of determinant of B, the alternating property for switching aj and aj plus 1, jth and j plus first column. Now, let's look at the deleted matrices. A1j, what is A1j? First row out, no problem there. Jth column out, so all the blue is out. So basically we are looking at something like this. All the blue is out, and also all the first row is out, so we have something like this. That's the same as B of 1j plus 1. B1, so remove the first row, no big deal, and j plus first, so all the blue is out, so we have only red. These two are the same matrices, so consequently we have to have the same determinants. Likewise, A1j plus 1 and B1j are the same. A1j plus 1, well here, first row is out, no big deal. J plus first, red is out, so we have only blue. And how about B1j? Jth is out, so all the red is out, we only have blue, as you can see here. So these two matrices are the same, so consequently, the determinants are the same as well. Now, how about the other deleted matrices, A1k and B1k? In that case, they have to be the same except for the sign. Why? Because this is just alternating property, because we switched jth and j plus first, and then we lost something else, anything else, so the switching stays. And then we are looking at the determinants of order n minus 1. Deleted matrices are square matrices of order n minus 1. So the inductive hypothesis works, and that's why I highlighted this part in green, inductive hypothesis part. So we have red, blue, and green, and let us make use of these in the determinant computation. Here we go. Here's determinant of A. We have A1k elements, so all the first row entry, and we have all these deleted matrices. Now we can decompose this sum into 3 pieces. K is equal to j, so A1j. K equals to j plus 1, so we have A1j plus 1, and then everything else. Now how about this A1j? That's the same as b1j plus 1. We saw that. And how about this a1j plus 1? That's the same as b1j. We switch those columns. And then a1j becomes a1j becomes b1j plus 1. Let's see, a1j is this one. And then b1j plus 1 is a1j because we switch the order. And then a1j plus 1, this one, is the same as b1j because we switch the order. So we have the matrices and then entries. What we didn't do, -1 to something power. So we used to have -1 to 1 plus j power here. But I would like to have j plus 1. So change it into j plus first power. So we just multiply by -1. So how do I undo that change? Extra negative. Same thing goes here. Used to be j plus 1, so we have j plus 1 here. But now b1j, so let's reduce it to 1 plus j. How do I reduce it? This is -1 to the first power. So how do I undo that? I need this negative sign here. How about everything else? Determinant of a1k, that's negative of determinant of b1k by the inductive hypothesis here. So we need this negative sign too. Consequence, everything fits with all negative. So what we have, summation of all these entries for matrix B and top row. So we have the negative of determinant of B. And this is a little bit tricky, so you may have to take some time comparing to understand everything. But not that hard. In short, we prove the alternating properties for two adjacent columns. Now what about arbitrary columns, two arbitrary columns? We have I and j, and let k be the difference, j minus a. So j is I plus k. So we have to move ai to the right k steps to reach the jth column. So how do I do that? First, switch ai and ai plus 1, like this. And that gave me negative sign. Next, ai and ai plus 2. The switching. So we have another -1. So -1 squared. Repeat, 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 all the way over to k steps. Finally, ai went to the jth column. We went k steps, so we want k sign changes, -1 to the k power. Alright, ai is in the right place now, jth column, so a j has to come back to I. That's going to take another k steps, right? Because k is j minus a. No, not really. It takes only k minus 1 steps. Why? When ai coming here, we switch the order, so aj is starting from not jth column, but j minus 1 column. So the difference is k minus 1. So it takes k steps for ai to get to the j, and for aj, it takes only k minus 1 step to come to ith column. So total, -1 to the 2k minus 1, that's always odd, so we always have to have negative sign. By the way, here's an example, just to help you understanding. I equals 3, j equals to 7, and k is 7 minus 3, 4. So, like this. And then I have to move a3 4 times, 4 steps to get here. And a7 is not starting from here, it's starting from here because of the final switching here. So a7 have to move 3 steps to the left. So we have 4 plus 3 is 7, always odd. Just an illustration. In general, always 2k minus 1. So we completed D2, the alternating property. Next, let's prove the multilinearity, and this is our strategy. Let's prove it only for the first column. So we have first column x, first column y for AB, and then ax plus by, let's call it C. And if you don't like those column vector forms, let's consider all those entry forms like this. And our aim is to prove that determinant of C, the linear combination, is A determinant of A plus B determinant of B. This is what we want to prove. Now from here, let's make some observations about the deleted matrices. A11, B11, C11, they're all the same because first row, come on, first row, no difference. First column, no difference. They're all C's, C2 to Cn, so they're all the same. How about C1j? In that case, first column always stays, something else will go out. So we have that. Alright. Let's go to the determinant computation for determinant of C. So first entry ax1 plus by1 times determinant of C11, and then everything else, starting from j equals 2 to the end. And then this determinant of 1c, this one, determinant C1j, this can be decomposed into A determinant of 1j plus B determinant of 1j. Why? Because of the inductive hypothesis. You see, this is deleted matrix, so this is order n-1. So yes, you can separate using the multilinearity for the determinants of order n-1. Now, how about all these? We can use the distributivity to get this determinants of C11 times determinant C11 times like this. And a C11, that's same as A11. And C11 is same as B11. So we can rewrite everything in terms of A's and B's. Here we go. X1 determinant A11, and that's for this, and then the deleted matrix. How about everything else? Everything else works just fine. The same thing goes to this B part. Y1, which is this one, times determinant of B11, this guy. Alright? And everything else, well, works out just fine. So what do we have? This is determinant of A, that's determinant of B. So we have A determinant of A plus B determinant of B. That's precisely what we wanted all along. So we proved the linearity with respect to the first column. Alright, let's use this to prove it for arbitrary column, and that's rather simple. Use the alternating property to move this ax plus by in arbitrary column into the first column. And then we can decompose those because we just proved that we have linearity with respect to the first column, so we can do it. We can decompose this linear combination. And then we can move those x and y back to their original places, jth column. And then once you do that, we're going to lose these negative signs. We earned this negative from first switching, and then we lost those from the second switching. So in the end, what do we have? We have this linear combination completely separated out. That means the linearity with respect to the jth column for arbitrary column. That completes the proof of the multilinearity and completes the proof of this entire theorem.